time we left off with a proof, or I guess we finished the lecture with a proof of the division algorithm. And I'm going to do an example in a second. Let me just remind you what that said. So it goes like this. If we have a couple of polynomials and what we require is that the coefficients live in a field. So if at little f and little g are polynomials with coefficients in the field f, and well, we need g of x, we need one of those polynomials to be non-zero, then there exist unique polynomials, say q of x and r of x, such that so f of x is going to equal g of x times some quotient q of x plus a remainder r of x. And r of x has to have degree in the appropriate range, so where the degree of r of x is strictly less than the degree of g of x. And this should, of course, remind you of the division algorithm that we have for integers, right? If you have two integers, one of them non-zero, so that you can always write a equal to b times q plus r, where r is between strictly less than b and greater than or equal to 0. Same idea here. What this does is it gets our polynomial, or our remainder, has degree in the appropriate range. It can be the 0 polynomial, and then it can have degree all the way up to, but not equal to, the degree of g of x, right? So same idea. In fact, if you remember, the proof of the division algorithm for integers required, well, I guess we use the well-ordering principle, which is equivalent to induction, which is what we used for the proof when we were working over a field. Okay, so let's try an example now. So let's let f of x equal x to the 4th plus x squared plus 2x plus 1, and g of x equals x squared plus 2x plus 1. Now, what I'd like to do is view these polynomials as living in Z3 bracket x, right? Now, I think you've done long division. I'm sure you've done long division, right? Back in algebra class. So back in high school, you learned to do long division with polynomials. And that's all the division algorithm is saying. It's telling you that long division works, right? That you can divide the polynomial f by the polynomial g, and you'll get a quotient and a remainder. That's what it says. And the division algorithm then goes on to say the remainder will lie in the appropriate range. So we're going to do this, and you did the same thing. It'll be the same as you did in high school, except we need to remember to do our arithmetic in Z3 rather than over the real numbers. Right? So the instructions here, let's say find q of x and r of x in Z3 bracket x as guaranteed by the division algorithm. And all this is telling us to do is to do long division. Right? It's telling us that long division works, and we're going to get a remainder in the appropriate range. So I want to divide x squared. Oh, you know, I wasn't clear. I guess I should have said, let me say, so I want it to go like this. I'm going to divide g of x into f of x. All right, so that would be, so I want f of x equal to g of x times q of x plus r of x. So I'm going to divide g into f. Remember, anytime if you have a missing term, so for example, I have no x cubed term here, remember to put one in by putting a 0 coefficient. Plus x squared plus 2x plus 1. Okay, so this is going to look and go just like you did in high school. x squared goes into x to the fourth. X squared terms. Multiply. X to the fourth. X squared times 2x, that'll give me a plus 2x cubed plus x squared, and then we subtract. Now, when I subtract, I'm going to get 0 here. I'm going to get negative 2x cubed here, which is the same as x cubed, right? Negative 2 in Z3 is equal to 1. And then we'll have plus 0x squared, bring down the next term. Right? So that's the one thing. Remember to do your arithmetic and end up with coefficients that actually live in Z3. So when I subtracted here, 0x cubed minus 2x cubed actually gave me a negative 2x cubed. But in Z3, negative 2, right, the inverse of 2, is what? Okay, now we do the same thing. So x squared goes into x cubed, x times, multiply, so we get an x cubed plus 2x squared plus x, subtract. This is going to give me a negative x squared, negative 2x squared, which is x squared. This will give me an x, and then what do? Bring down the 1. X squared goes into x squared one time. Multiply this out, x squared plus 2x plus 1, subtract. That's going to give me negative x, right? Negative x, which is the same as 2x. All right, so what do we get then? What this tells us is that x to the fourth plus x squared plus 2x plus 1 is equal to my quotient, right? So there is my q of x, and there's my remainder. So it's going to equal g of x is x squared plus 2x plus 1. Q of x is x squared plus x plus 1 plus r of x, which is 2x. And you can actually check, multiply this stuff out, combine terms, and you're going to get that polynomial right there. All right, so there's the division algorithm in action. Now, what we're going to see, what we're going to get today, are a bunch of corollaries to the division algorithm. Right? And so, the first one, so this will be corollary 23.2. This one has a name, it's called remainder theorem. And it goes like this. If we take some polynomial f of x in f bracket x, and alpha is an element of that field, then the remainder when dividing f of x by the polynomial x minus alpha is exactly the constant f of alpha. So for the proof, right, I'm just going to apply the division algorithm. And so there's something to show here. So we write f of x according to the division algorithm. It can be written as x minus alpha times some polynomial q of x plus some polynomial r of x, where the degree of r of x has to be less than the degree of our divisor right here at x minus alpha, and so the degree has to be strictly less than 1. That means that r of x has to be a constant polynomial. Either it's going to have degree 0 or degree minus infinity. Okay, so then let's see, what do we know? Well, what I want to do is I want to plug alpha into both sides. And so what are we going to get? We're going to get f of alpha equals 0 times q of x plus r of alpha. Now, this is a constant polynomial right here. R of alpha is constant, right? And so it has to actually be equal to f of alpha. So what we have is r of x is a constant polynomial, right? So we can say, so r of x is a constant, and so it has to be equal to f of alpha. Thus, right, so we can say thus f of x is equal to x minus alpha times q of x plus f of alpha, right? Okay, so there's the first consequence of the division algorithm. Here comes the next one. So this will be corollary 22.3, and this one has a name also. It's called the factor theorem. And it goes like this. So if, well, I'll say let f of x be an element of f bracket x and alpha some constant, some element of f. Then f of alpha equals 0 if and only if x minus alpha is a factor of f of x. Okay, and for the proof, so for our proof, in the forward direction, let's assume that we have f of alpha equal to 0, right? So we can write this, right, f of x equal to x minus alpha times q of x plus f of alpha. Remember, that was the, that's the factor theorem, not the factor theorem, the remainder theorem. So then if f of alpha equals 0, right, if that's our assumption, then what we have is f of x can be written as x minus alpha times some other polynomial. Right, so x minus alpha times q of x as desired. In the reverse direction, so if f of x has x minus alpha as a factor, that means f of x is equal to x minus alpha times q of x. Then, of course, if I compute or if I plug alpha in, f of alpha is equal to 0 times q of x, which equals 0. Okay, so that completes the proof of that corollary there. Okay, I want to cover two more consequences of the division algorithm. So the next one, this would be corollary 22.4. And so we say, let's let f of x be a polynomial with coefficients in the field f. And I don't want f to be the zero polynomial. So I need the degree of f of x to be greater than or equal to 0. Right? So it can be a constant polynomial, but I don't want it to be the zero polynomial. So then f of x has at most n zeros in f. Now for the proof, so let's just take it. Let's start off with a 0. So let's let alpha 1 in f be a 0 of f of x. Now, by our previous theorem, by the factor theorem, f of x is equal to x minus alpha 1 times, what do I want to call it? Q, yeah, let's call it q sub 1. Where q sub 1 of x is in f bracket x. And what do we know about the degree of q1? Well, it's got the product here has to match the degree over here. We've got degree 1. This has to be degree n minus 1. So we can say and the degree of q1 of x equals n minus 1. Now, right. So now let's take another 0. So if alpha 2 is a 0, and I should be clear, alpha 2 is not equal to alpha 1. So if alpha 2 not equal to alpha 1 is a 0 of f of x, then when we look up here, what do we have? Plug alpha 2 in here, we'll get non-zero. That forces alpha 2 to be a 0 of q1. All right, so then q1 of alpha 2 equals 0. So, yeah, when we write this out, we'll have f of x equal to x minus alpha 1. And now I'm applying the factor theorem to q1, which would give us x minus alpha 2 times q2 of x. And then you can repeat this process, right? So continue. Oh, and I should say, whoops, where the degree of q2 of x is now going to be n minus 2. Right? So each time you find a new 0 of f of x, you get a new factor according to the factor theorem. So continue this process. And how far can you actually go? Well, the farthest you can go, right? So continue this process to get f of x equal to x minus alpha 1, x minus alpha 2, and we'll keep going. X minus alpha k times q sub k of x, where now we don't have any more zeros. So where q sub k of x has no zeros in f. Now, let's see, since, I'm going to say this, So what have we found now? We found k, and I should say here, so note that k is going to be less than or equal to n. It's possible that this polynomial right here is just a constant polynomial, right? But at some point then this process stops, and so what do we have? Here are the zeros, and when you plug any other element of f in to this polynomial, on the right-hand side, you're not going to get 0, which means you won't have any more zeros for f. So we can say f of beta is not equal to 0 for all beta in capital F. Right? So we have at most at most n, we have exactly k zeros, which means at most n zeros to our polynomial. Okay, and I want to do one more consequence of the division algorithm. So this is going to be corollary 22.5. So let's let f be a field, and so let f be a field if G is a finite subgroup of f star. So remember, f star, that's the non-zero elements of f. It's going to be an abelian group, right? So, right, under the multiplication, under the operation of multiplication, right? So then, G is cyclic. This just sort of comes out of nowhere, right? Well, here we are talking about polynomials, and all of a sudden we get this result about groups, right? Subgroups of a, or let's say finite subgroups of field have to be cyclic. So let's see now. What do I know? G is a finite subgroup of this abelian group right here. All right, so since G is a finite abelian group, we know something about the structure of finite abelian groups. There exists, say, G1 up through, what do I use here? G sub k. So G1 ... gk in capital G, such that G is equal to cyclic subgroup generated by G1 cross cyclic subgroup generated by G2 cross ... cross cyclic subgroup generated by GK, and we know something about the orders of each of these. So what am I doing? I'm applying the fundamental theorem of finite abelian groups. All right, so we know that our finite abelian group can be expressed as an internal direct product of cyclic groups, and I can say here where. Now, what do we know about the orders of these? Each one of these has order a power of a prime. So let's say where the order of Gi is going to be P sub I raised to the N sub I for some primes P sub I, and these will be natural numbers N sub I. Okay, so now let's let m be the least common multiple of these orders. So it would be the least common multiple of the powers, yeah, so P1, N1, P2, N2, PK to the NK. Now, what does that tell us then? Well, one thing we know is that m is going to be less than or equal to the product of all of these powers of primes here. Let me just say, so m is less than or equal to P1, N1, P2, N2, dot, 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 P sub K, N sub K. Now, what does that tell us? So then, g raised to the m is equal to the identity, which is 1, for all g in capital G, right? The least common multiple of this is going to give us, right, if you take the least common multiple, right, the order of any element, I don't want to say this, the order of an element is the least common multiple of the product. And so that means that g raised to this least common multiple is going to give us the identity for every choice of element in there. Let's see, I want to continue this. And so the polynomial, say f of x, we knew we had to bring polynomials in here somewhere, f of x equal to x to the m minus 1 has at least well, every element in here has to be a 0, and so that would mean at least order of g, which equals P1 N1 dot 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 PK NK zeros. So what does that say? Has at least that many zeros. And then so by corollary, 22.4, m has to be greater than or equal to this number right here also. So it has to be greater than or equal to the order. So P1 to the N1 dot 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 PK to the NK. And so what does that tell us? It tells us that m has to equal that. You can say, and so m is equal to P1 to the N1 dot 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 PK to the NK. So what? Well, so that tells us then, right, if we think about how you'd compute the least common multiple here, it tells us that all of these primes have to be distinct. So it follows that the P sub I are distinct which means that the orders of these right here are relatively prime. Well, if the orders of each of these component subgroups is relatively prime, then we know from last quarter, right, that we have a cyclic subgroup whose order is equal to the product of these orders. So therefore, G is isomorphic to Z sub n. So let me recap that one. This one's a little bit, I don't know, it's just kind of an unexpected proof, but once you see it, or once you've seen it, it's actually pretty fun. Okay, so what just happened here? Let me kind of give you a little recap. Every finite abelian group is a product of cyclic groups. All right, that's the fundamental theorem of finite abelian groups. And we can say a little bit more. What do we know about these cyclic groups? Each of these cyclic groups has product of prime, right? Right, so the orders of these, we've got our generators here, and the orders of each of these groups has to be a power of a prime. But notice here, we didn't require these primes to be distinct, right? So for example, this one could be, have order 2 cubed, and this one could have order 2 to the 4th, right? That was not ruled out by this. And then we said, okay, let's just call this number m. That will be the least common multiple of the primes. Okay, so then we know that anytime if we take any element and raise it to the least common multiple, right? Remember how to compute orders of elements inside a cyclic group, product of cyclic groups, right? It is the least common multiple of the orders of the component groups. So that guarantees us then that the order of this element, or let me say this better, that tells us that no matter which element G we choose, when we raise it to the least common multiple of the orders of these groups, we're guaranteed to get the identity. Okay, now we can bring in polynomials. That means that no matter which G we substitute, we're going to get 0 in this polynomial. So every element of the group gives us 0. Okay, so by our previous theorem then, how many zeros can we have? We can have at most m zeros to this polynomial. So that tells us then that m has to be bigger than the number of elements in the group. So now, taking these two inequalities together, that forces us to conclude that m is equal to the product of these primes. Well, if the least common multiple is equal to the product of the primes, that means that there can't be any repeats from these primes in here. Right? That tells us then that the primes are distinct. And then we know that a product of cyclic groups is cyclic if and only if the orders of those cyclic groups are relatively prime. Well, we've got orders relatively prime, and so that means that G has to be isomorphic to the cyclic group that we get, or whose order is the product, or the product of the orders of the constituent groups. Okay, so study this one. This one, I don't know, it's fun. I don't know that I did the greatest job explaining it. I think I got stuck a couple of times here, but hopefully this makes sense once I did the recap, okay? So ask questions in office hours, or I wish you were here to ask me questions right now, but unfortunately you're not. So let's stop here and we will see you next time, okay? Bye.